You've been following 3i Atlas for a while. You know it's a massive, extraordinarily fast object moving toward the Sun. You've also heard that it's the third interstellar visitor ever detected, and by far the strangest one. But what you probably don't know is what happened on October 29th, 2025. That day, Atlas reached its closest point to the Sun, the perihelion, and then quickly slipped behind our star. It hid. It became unobservable. For nearly 4 to 6 weeks, no telescope on Earth could image it. This period is known as the solar conjunction, and in astronomy it's equivalent to being plunged into darkness. No ground-based telescope can see through the Sun's glare. No space telescope can point that close to the solar disk without risking its instruments. And during that time, Atlas was truly invisible. And according to Harvard astrophysicist Avi Loeb, this wasn't a coincidence. He believes it was an opportunity. The perfect moment to use the Sun's gravitational pull to enter a permanent orbit, to trap itself within the solar system forever. Loeb called this possibility the maneuver window, the point of no return. And now, 7 days have passed since that day, but we still don't know exactly what happened. In his latest interview, Loeb said something that sent chills through the research community. Take your vacation before October 29th. It wasn't a warning for those who wanted to observe Atlas. It was as if he implied that something would fundamentally change after October 29th, that there would be no turning back. And here's where things get truly intriguing. Atlas didn't just pass near the Sun at a convenient time by coincidence. On the day it reached perihelion, Earth was positioned exactly on the opposite side of the Sun. The geometry was nearly perfect. Between us lay a 150 million kilometre wide star, the Sun, and this arrangement looked almost deliberately designed. If someone wanted to make a trajectory correction without being detected, this would be the exact moment to do it. This alignment, this flawless configuration, would be deliberately chosen. So far, we've analysed orbital mechanics, the Oberth effect, and the observation blackout that began on October 29th and lasted until late November. Now it's time to talk about what Atlas might have done behind that curtain of invisibility, why its timing was so precise, how such a low probability alignment occurred, and what it would mean if Atlas reappears from behind the Sun no longer on an escape trajectory. Because whether you believe this is a purely natural astronomical event or the result of something more deliberate, more intelligent, one thing remains constant. Something may have happened on October 29th. The maneuver window opened that day, and we cannot look inside it. Let's begin. But first, if you enjoy deep space analyses like this, don't forget to hit the like button, subscribe, and tell us in the comments where you're listening from, what time it is there, and whether you think Atlas kept moving away after October 29th. Now, let's continue. Solar conjunctions aren't rare events. Every planet experiences them periodically as it orbits the Sun, passing behind it. For example, Mars enters solar conjunction roughly every 26 months, and Venus every 19 months. During these few weeks, communication with those planets and their spacecraft is cut off. That's because radio signals must pass through the Sun's corona, a dense plasma layer that distorts and fills them with interference. That's why NASA always plans missions with these conjunction periods in mind, scheduling critical operations either before or after them. But a solar conjunction involving an interstellar object passing through the inner solar system is completely different. It's not periodic. It happens only once. Everything depends on the object's trajectory and on Earth's position in space at that exact time. For Atlas, that moment was October 29th, 2025, and the alignment was truly extraordinary. When Atlas reached its perihelion, its closest point to the Sun, Earth was exactly on the opposite side. The Sun stood precisely between us and Atlas, not a degree to the right or left, perfectly centred. Harvard astrophysicist Avi Loeb calculated the probability of such an alignment occurring by chance. He took Atlas's orbit, determined from thousands of telescope observations, and adjusted its velocity by just a tiny amount. If it had been moving only a few meters per second faster or slower, its time of perihelion would have shifted by days or even weeks, and that small difference would have completely changed Earth's position. And when time shifts, everything changes. because Earth moves around the Sun at 30 kilometers per second. If Atlas had reached that point just one day earlier or later, Earth would have moved 2.6 million kilometers along its orbit. In that case, the perfect alignment would have been lost. Atlas wouldn't have been directly behind the Sun, only partially obscured, visible at a faint angle. Loeb reran the probability, accounting for orbital uncertainties. The result was striking. The chance of Atlas reaching perihelion, its closest point to the Sun, exactly during solar conjunction, with Earth on the opposite side, was roughly 1 in 50. Not impossible, but highly unlikely. Another peculiarity to add to Atlas's list: its size, orbit, timing. Each might seem like coincidence alone, but together they form a pattern that's hard to ignore, almost the impression of deliberate design. That's why October 29th is so critical. Perihelion, the closest point to the Sun, is the ideal location for a braking maneuver. It's a basic truth of orbital mechanics, the Oberth effect. Every spacecraft humanity has sent to the outer solar system has used this principle. When an object moves rapidly within a strong gravitational field, even a small thrust produces a huge change in velocity. If you fire your engines at perihelion, the gain, or in this case, loss, in orbital energy is unmatched anywhere else. Cassini used this effect to reach Saturn. Voyager used it to escape the solar system, and if Atlas wanted to do the opposite, to slow down and settle into a stable orbit around the Sun, then October 29th was precisely the right moment. This kind of maneuver is called a retrograde burn, firing in the opposite direction of travel to reduce speed. If an object is on a hyperbolic trajectory, fast enough to escape the Sun's gravity, even a small decrease in velocity can have dramatic consequences. It ceases to be a fleeing visitor and becomes a permanent resident on an elliptical solar orbit. The required change in speed depends on the object's velocity and proximity to the Sun. For Atlas, the conditions were extremely delicate. At perihelion, about 1.4 astronomical units away, it was moving at roughly 60 kilometers per second. According to Loeb's calculations, a reduction of just 2-3 kilometers could have been enough for Atlas to be captured by the Sun's gravity and settle into a permanent orbit. A difference of 2-3 kilometers might not sound like much. For comparison, the escape velocity from Earth's surface is 11 km/s, but achieving even that smaller change requires tremendous energy, especially for an object as large as Atlas. Based on orbital analyses and its stable motion without visible outgassing, Atlas's mass is estimated at no less than 33 billion tons. That's an enormous body moving at 60 kilometers per second, its kinetic energy beyond imagination. Altering that speed even slightly would require immense thrust. If Atlas is a natural comet, it has no engines. A deliberate maneuver would be impossible. But if it's not natural, if it's a technological construct, then the timing of October 29th makes perfect sense. Because at your closest and fastest point to the Sun, you can use its gravity most efficiently, and all while the most advanced telescopes on Earth are hidden behind the Sun's glare. No one can see you. 1 million kilometers of plasma and magnetic fields completely conceal you, as if you've vanished from the eyes of the universe itself. Loeb isn't saying Atlas definitely performed a maneuver. He presents it as one possible scenario, but he emphasizes how convenient the alignment is, almost millimetrically precise. That's why he insists the period before and after October 29th must be carefully monitored. If a maneuver did occur, we won't see it directly. We'll only notice later, when Atlas reappears from behind the Sun in late November and its orbit is recalculated. In fact, this blackout period is even longer than the conjunction itself. Solar conjunction lasts about 2 weeks, when the Sun is directly between Earth and Atlas. But the Sun's brightness interrupts observations much earlier. Even if Atlas is technically visible, its proximity to the Sun overwhelms any image. Ground telescopes can't look that close without damage, and space telescopes like Hubble or Webb are forbidden from pointing near the Sun for safety reasons. As a result, we lose sight of Atlas by mid-October and won't see it again until late November or early December. That dark period, the 6 weeks no telescope can observe, may be the most critical time of all. 6 weeks. That's our window of total blindness, and during those 6 weeks anything could happen. If Atlas is motionless, an ordinary comet, nothing changes. It will curve around the Sun and continue outward on its hyperbolic path. When it reappears in December, if its position matches predictions, no manoeuvre occurred. But if its orbit doesn't match, if it appears in a different location or moves at a different speed, then something happened. Because orbital mechanics are deterministic, there are no coincidences. Without an external force, an orbit cannot change. If Atlas's trajectory shifts, there are only 2 explanations. Either a natural gas outburst, for which there's no sign so far, or an artificial thrust, a deliberate act. And that's what makes this scenario unsettling. If Atlas really performed a manoeuvre on October 29th and entered solar orbit, we may not have much time to respond. In that case, the object would return toward the inner solar system, potentially passing close to Earth in December or early 2026. According to Loeb's calculations, if Atlas transitions from a hyperbolic to an elliptical orbit, circling the Sun roughly at 1 astronomical unit, the Earth-Sun distance, it would return every few years, and one of those passes could bring it alarmingly close to Earth's orbit. That doesn't mean a direct collision course, but close enough for us to witness what it truly is. And that's where the most chilling question arises. If Atlas chose to stay in the solar system, why? Was its purpose merely observation, resource collection, or something entirely beyond our understanding? Loeb has previously suggested that interstellar probes could use gravitational assists and orbital captures to efficiently survey multiple star systems, slowing down to observe, then speeding up to move on. If Atlas is truly such a probe, then October 29th may not have been the end of a brief flyby, but the beginning of a long stay. But there's also a darker interpretation. If Atlas is technological, and it chose to remain, maybe it did so because it discovered something. Maybe it found us. Maybe it detected our radio transmissions, the glow of our cities, the organised orbits of our satellites, or the chemical signatures in our atmosphere from 8 billion humans burning fossil fuels. All of this would be detectable to a sufficiently advanced observer, even from interstellar distances. If Atlas detected such signals and adjusted its trajectory accordingly, then October 29th wasn't just a manoeuvre window, it may have been the beginning of first contact. Slow, uncertain, but inevitable. Avi Loeb addressed this possibility directly. He said humanity must be prepared for both outcomes, that Atlas is natural or that it's technological. He argued it would be a mistake to dismiss the technological hypothesis without evidence, because if we're wrong, if Atlas really is a probe and we mistake it for an ordinary comet, then we might be throwing away the greatest opportunity in human history. It would be a chance to learn, to communicate, to begin a dialogue for the first time, and that chance might never come again. Interstellar visitors are extremely rare. Atlas is only the 3rd confirmed in human history. If it truly is technological and we ignore it, we might be discarding the answer to humanity's oldest question: are we alone in the universe? As of now, the time this recording is made, 6 days have passed since October 29th. Atlas has already reached perihelion and disappeared behind the Sun. We're now in the waiting period, the silent weeks when no telescope can see it. Observatories around the world allocated time before conjunction to record its position, speed, brightness, and spectral signature with extraordinary precision, to have a perfect baseline before the blackout. That way, when Atlas reappears, any slightest change can be detected immediately. But that's the key issue. No matter how perfect the before and after data are, we'll never directly know what happened in between. We can only infer from the results. We won't see the manoeuvre itself. If propulsion was used, we'll never detect its trace. At the most critical moment, we are completely blind. And if Loeb's hypothesis is correct, this blindness is not accidental. It's a deliberately designed gap. The timing, the alignment, Earth being exactly on the opposite side, all of it together suggests the trajectory might have been planned, that the solar conjunction was used intentionally to hide. What makes the Atlas story truly disturbing is not a single event, but a chain of probabilities. Each one alone can be explained, but together they no longer feel random. its orbit's near-perfect alignment with the ecliptic plane, its close passes to Mars, Venus and Jupiter, its suspiciously high mass for its size, implying a hollow or structural interior, its chemical composition which matches no known comet, and now the most striking factor, timing. Perihelion coinciding with solar conjunction, the perfect moment to manoeuvre unseen. Yes, each piece of data could fit a natural explanation. The universe is strange, we could say. Coincidences happen. But at some point, these coincidences pile up so precisely that randomness becomes less likely than intention. The physics behind the manoeuvre window on October 29th isn't just speculation. It's the very orbital mechanics that have formed the basis of every spacecraft humanity has ever sent into space. And to understand why this particular moment was so critical, we have to look at one of the most powerful but also most counterintuitive concepts in spaceflight, the Oberth effect. The Oberth effect says that a propulsion maneuver gives the greatest result when it is carried out at the point in the orbit where the object is moving the fastest. At first glance, this seems illogical. You might think, if I apply thrust, don't I get the same change in velocity, delta V, no matter when I do it? Fire your rocket for 1 second while you're moving at 10 km, or fire it for 1 second while you're moving at 50 km. It looks like you'd get the same result. But orbital mechanics doesn't work like that. The energy a body gains depends not only on the change in velocity, but also on the speed it already has at the moment you apply that change. Here's the mathematical reason. An object's kinetic energy is defined as half its mass times the square of its velocity. When an object accelerates via thrust, you're actually adding kinetic energy to the system. But the critical point here is that this energy increases with the square of the speed. So applying the same delta V, the same change in speed, at high velocity gives you far more energy than applying it at low velocity. For example, when a spacecraft travelling at 50 km/s increases its speed by just 1 km/s, it gains far more kinetic energy than a spacecraft travelling at 10 km that increases by the same amount. And that's exactly why, in orbital mechanics, energy is the fundamental factor that determines whether an object remains bound or escapes into interstellar space. For Atlas, perihelion, its closest point to the Sun, was also its point of maximum speed. As it approached the Sun, gravity kept accelerating it. When it reached about 1.4 astronomical units, a distance corresponding roughly to between the Sun and Mars, Atlas was moving at about 60 kilometers per second relative to the Sun. That is an extraordinary speed. For comparison, Earth orbits the Sun at 30 kilometers. Voyager 1, the fastest spacecraft humanity has ever launched, even after 47 years of travel and multiple gravity assists, is moving at only about 17 kilometers relative to the Sun. Atlas, at perihelion, was moving 3 times faster than Voyager. At that speed, even the smallest change creates an enormous energy difference. If Atlas had fired forward-facing engines and reduced its speed by just 3 km/s, its total energy would have dropped below the Sun's escape energy. And at that moment, instead of continuing on a hyperbolic trajectory outward from the solar system, it would have shifted into an elliptic orbit bound to the Sun, a permanent captured orbit. Such a maneuver wouldn't require an impossibly huge thrust. It would only require perfect timing and a small but precisely applied delta V at the right moment. Loeb calculated the conditions needed for this maneuver using Atlas's observed orbit and mass. Based on the lack of any signs of external acceleration in observations, he assumed a minimum mass of about 33 billion tons. If you slow this mass, travelling at 60 km/s, by just 3 km/s, the change in kinetic energy is on the order of 1.5 1020 joules, which is roughly equivalent to 35,000 megatons of TNT. In absolute terms, that's a gigantic number. Yet if there is an advanced propulsion system with suitable fuel and technology, it is not unattainable. For comparison, each Saturn V launch, the rocket that sent humans to the Moon, released about 1013 joules of energy. So the energy Atlas would need is roughly equal to 15 million Saturn V launches, which sounds impossible, but these calculations do not assume a chemical rocket. If Atlas is a probe designed to travel interstellar space over millions of years, It could be using ion engines, fusion propulsion, antimatter, or some other high-energy density propulsion technology we don't yet know about. That is, something far more efficient and energy-dense than the discrete systems built by humans. The key point here is this: the maneuver is physically possible. It isn't easy. It certainly isn't simple. But if Atlas is truly a technological object and has a propulsion system, then it is possible. And October 26th was the most favourable time to do it. At any other point in the orbit, achieving the same result would have required a much larger delta V. Earlier in the approach, Atlas was still slower and farther from the Sun, so the Oberth effect advantage would have been much smaller. Later, that is, after perihelion, the object would already have been moving away from the Sun, which means reversing direction and slowing down would have required much greater thrust. That's why perihelion is known as the sweet spot in space mechanics. It's that perfect moment when gravity and velocity combine to make orbital capture most efficient. But what makes October 29 special isn't just the physics, there's also the observation blackout. If you're going to perform a maneuver, you want to do it at a time when no one can watch you. Not because the maneuver would be visible to the naked eye. Seeing a rocket plume from millions of kilometers away is nearly impossible. But changes in orbit can be computed from later observations. If astronomers can observe Atlas before and after the maneuver, they can tell from the difference in orbit that thrust was applied. However, if the maneuver happens during solar conjunction, that period when observations from Earth are impossible, its detection is delayed. By the time we notice, weeks will have gone by. Atlas will already have changed direction, the geometry will be completely different, and our ability to respond will be much more limited. That's why Loeb's warning, "Take your vacation before October 29th, carries such an ominous meaning. Whatever happens during conjunction, whether Atlas does something there or not, the situation may change irreversibly. If the maneuver succeeds, Atlas enters solar orbit, meaning it's no longer leaving, it's staying. And for us, that means much more than a simple observation opportunity. It means shifting from watching a temporary visitor to coexisting with a permanent presence in our cosmic neighbourhood." The geometry of solar conjunction also raises suspicion because such a precise alignment is extremely rare. Atlas doesn't just reach perihelion near the Sun, it does so at the exact moment when Earth is on the opposite side, at 180 degrees. This is called superior conjunction, and it's the worst-case scenario for observation. The Sun sits exactly between the observer and the target. Brightness and interference peak. If you want to plan an orbit in secret and hide from Earth-based observations, a superior conjunction at perihelion is the ideal scenario. Loeb also calculated how rare this alignment is. He took Atlas's known orbit and asked, if we randomize the time of arrival, how often would it reach perihelion while in superior conjunction with Earth? The answer depended on how wide you define the conjunction window. If you demand a perfect alignment, the Sun, Earth and Atlas exactly on the same line, the probability is almost zero. But if you allow a few weeks tolerance during which observation is still severely impeded, the probability comes out to about 2%, i.e. 1 in 50. Rare, but not impossible. However, that 2% probability assumes the arrival time is completely random. It assumes Atlas's orbit was not chosen specifically to achieve this alignment. But what if it was? If this orbit was intentional, if Atlas, or whoever sent it, planned this approach specifically to use solar conjunction as cover, then the entire probability calculation becomes meaningless. You're no longer asking, what are the chances a random object shows up in this window? You're asking, would an intelligent agent choose this window for strategic reasons? And the answer is obvious. Yes, it would. This is basically a fine-tuning argument applied to orbital mechanics. If one event is unusual, you call it coincidence. If 2 events are unusual, you get curious. But if 10 events are unusual, and they all point in the same direction, you stop thinking random, and you start thinking deliberate. Atlas is standing exactly at that point. It has too many unusual properties. Its size, its mass, its chemical composition, its orbit, its timing. Each one can be explained on its own. But when you put them side by side, the overall pattern looks less like nature and more like engineering. Now, if we could actually observe this maneuver, Let's talk about what it would look like. Right now, we can't see it directly because of solar conjunction, but understanding the mechanism helps us know what to look for when Atlas reappears in November. A retrograde burn performed at perihelion, that is, thrust applied opposite to the direction of motion, creates several distinct observable effects. First, the change in speed. Atlas was moving at about 60 kilometers relative to the Sun. If, as Loeb estimated, a delta V of about 3 kilometers was applied, that speed would drop to 57 kilometers. That's about a 5% reduction, a difference measurable with high-precision tracking. Second, the change in orbital energy. Atlas would transition from a positive energy, hyperbolic orbit, a trajectory that can completely escape the Sun's gravity, to a negative energy elliptic orbit, meaning it is now bound to the Sun on a permanent path. Third, the orbital period. A hyperbolic orbit has an infinite period. An object on such a path never returns, but an object on an elliptic orbit completes its circuit around the Sun in a certain time. So if Atlas really braked, it may no longer be a passerby, but a new resident of the solar system. The exact orbital period would depend on the magnitude of the velocity reduction and the distance at which it was performed. If Atlas, at 1.4 AU, roughly Sun-Mars distance, reduced its speed by 3 kilometers, the resulting orbit would have a semi-major axis of about 5 AU, close to Jupiter's orbit. In that case, the new orbital period would be about 11 years. That would mean Atlas would return to the inner solar system every 11 years, crossing Earth's and Mars's orbits again. Each return would mean an opportunity for close observation, attempted communication, and, if Atlas is a responsive system, interaction. But here's the tricky part. We won't be able to know that orbital period immediately. To determine an orbit precisely, you need to measure the object's position multiple times over time and fit those measurements to an ellipse. For a newly captured object, this process can take weeks, sometimes months. When Atlas emerges from behind the Sun in late November, we'll have only one data point, its position at that moment. We will compare that position to the position we predicted before solar conjunction. If there's a discrepancy, we will know something changed. But mapping out the full orbit will take weeks. During that tracking period, uncertainty will persist. Maybe Atlas really did make a small maneuver and only slightly altered its path, so it wasn't fully captured, but bent its trajectory a bit. Maybe it made a large maneuver and is now on a high elliptic orbit that will bring it back into the inner solar system in a few months. Or maybe it did nothing at all and is moving exactly as predicted. There's only one way to resolve this uncertainty: continuous observation. Measuring Atlas's position and velocity with ever-increasing precision. That's why Loeb stresses how critical pre-conjunction observations are. The better we know Atlas's orbit before it goes dark, the more clearly we can detect even the smallest changes afterward. If we had millimeter-level position data from before October 29th, then even the tiniest deviation in November would be detected. But if the data are uncertain, if the measurements have a margin of error, small maneuvers could go unnoticed. And in that case, Atlas could slowly adjust its path to plan a close pass by Earth or Mars, and we would only realize it months later, after it had already made the move. There is also the question, what kind of propulsion system could Atlas be using? Because different propulsion technologies leave different traces, and each has its own detectable signature. Chemical rockets expel hot combustion gases. These plumes create short-lived flashes in both infrared and visible light. Ion engines are much quieter, but produce beams of charged particles. These beams can be detected through electromagnetic waves or anomalies in the radio spectrum. Nuclear thermal or fusion propulsion systems are far more powerful. They emit intense heat and radiation, forming a clear energy signature for long-range detectors. If Atlas is truly using one of these systems, then even during solar conjunction, when it cannot be seen from Earth, it could still be detected indirectly by spacecraft or deep space observatories that have a line of sight to the far side of the Sun. In short, invisibility isn't impossible, but it requires the right observer in the right place at the right time. For example, NASA's Juno mission is currently in Jupiter's orbit, and during Atlas's perihelion passage, it will be on the opposite side from Earth. Juno was not designed to observe Atlas, but if Atlas releases a strong burst of energy, Juno's sensitive plasma, magnetic field, and radiation instruments could detect the anomaly indirectly. Similarly, ESA's JUICE spacecraft is currently on its way to Jupiter and will be in a position in late October to partially see Atlas. These spacecraft are not specifically tracking Atlas, but if Atlas performs a large-scale maneuver, for example, releases ion exhaust, increases radiation, or triggers a plasma wave, these effects could appear as momentary anomalies in Juno or JUICE data. So even if Atlas is hidden from Earth, it could still betray itself through indirect signatures to observers on the far side of the Sun. Of course, all these possibilities assume that Atlas is using some kind of conventional, for us, propulsion that emits detectable radiation. But if Atlas is using a propulsion technology we don't yet understand, one that doesn't emit radiation, or that our current sensors cannot detect, then the maneuver would be completely invisible. We would only notice it indirectly through changes in its orbit, and that too weeks after the fact. And by then, everything would already be over. Atlas would either have entered solar orbit or it wouldn't. While we were still trying to observe, because of the light time delay and the observation gap caused by solar conjunction, we'd be responding to something that actually happened weeks earlier. So it may well be that Atlas has already made its decision, and we will only learn about it from the echo of the past. The observational blackout that began on October 29th doesn't literally mean we can't see anything at all. We're not completely blind, but the limitations are so severe that detecting a small maneuver that may have happened during conjunction becomes almost impossible. Understanding these limitations explains why this window is so critical, and why AV Loeb kept insisting we have to monitor Atlas as tightly as possible before it disappears. First, ground-based telescopes began to lose Atlas. By mid-October, as the object approached perihelion and the angular separation between Atlas and the Sun, as seen from Earth, dropped below 10 degrees, observations quickly became difficult. The Sun's intense brightness was drowning out everything near it, especially faint objects like Atlas. Even the most powerful telescopes that can mask the Sun's light with a coronagraph run the risk of damaging their optics and detectors if they point just a few degrees closer in. By October 20, just 9 days before perihelion, most major observatories on Earth were no longer able to track Atlas reliably. Space telescopes had a slight advantage over ground-based ones, but only a slight one. They too have their limits. The Hubble Space Telescope has very strict pointing rules to protect its instruments from intense solar radiation, so Hubble cannot observe any target closer than 50 degrees to the Sun. For Atlas, that means Hubble loses it in early October and can't see it again until more than a month after perihelion, toward the end of November. The situation is even more restrictive for the James Webb Space Telescope. Webb operates in infrared wavelengths, and the Sun is extremely bright in those wavelengths. Its giant sun shield must always stay between the Sun and the telescope to protect its sensitive instruments. Because of this, Webb cannot observe any object closer than 85 degrees to the Sun. As a result, Webb loses Atlas even earlier than Hubble and can only observe it again in December, once it has moved far enough away from the Sun. So when Atlas slipped behind the Sun, humanity's two most powerful eyes went dark at the same time. That left only a handful of spacecraft located in the inner solar system, or en route to the outer planets. Chief among these is NASA's Juno probe, currently in orbit around Jupiter. Juno is about 5 astronomical units from the Sun, and, during Atlas's perihelion passage, will be on the opposite side from Earth. Of course, Juno wasn't designed to observe interstellar objects. Its mission is to study Jupiter's atmosphere, magnetosphere, and interior. Still, its cameras and spectrometers could in theory image Atlas if it passed through this field of view. But there's a problem. The geometry isn't favourable. Juno is well above the ecliptic plane that Atlas is following, and its orbit around Jupiter is at a high inclination. Therefore, around late October, Juno doesn't have a direct line of sight to Atlas. It might catch a very brief snapshot if Atlas's position happens to coincide with the direction Juno is looking at that exact moment. But continuous tracking or motion capture is nearly impossible. ESA's JUICE spacecraft, the Jupiter Icy Moons Explorer launched in 2023, is taking a long route to Jupiter. Along its mission path, it uses gravity assist from Earth and Venus to gain speed. By late October 2025, JUICE will be somewhere between Earth and Mars, that is, moving through the inner regions of the solar system. It carries an extensive set of scientific instruments, cameras, spectrometers, radar systems. But just like Juno, JUICE was not built to track a fast interstellar object moving at 60 km/s. Its observation cadence is slow because its goal is to conduct long-term studies of Jupiter's icy moons, so tracking fast targets doesn't match the way the system is designed to operate. If, by chance, JUICE happens to be looking exactly in the direction Atlas is passing, it could theoretically capture some incidental data. But that would only happen if mission control explicitly made Atlas a priority, and that would mean deviating from JUICE's primary science goals. So while technically possible, it's a very low probability scenario in practice. The most promising platform to observe Atlas during solar conjunction is actually NASA's Parker Solar Probe. This spacecraft was designed to get closer to the Sun than any probe before it. Its mission is to study the Sun's corona, the outer atmosphere, and it carries advanced sensors that can image the Sun's surroundings in visible light and extreme ultraviolet (EUV). At the end of October 2025, Parker will be only a few million kilometers from the Sun. That's a far more interior orbit than Atlas's 1.4 AU, about 210 million kilometers perihelion distance. So while Parker is skimming right past the Sun, Atlas will be much farther out, but along the same general line of sight. From that vantage point, Parker could see something Earth-based observers can't. It could, in principle, look outward through the Sun's glare and spot Atlas. In other words, while we can't see anything because of the Sun's blinding light, Parker is the one observer sitting right inside that light and could notice Atlas. But there's a serious issue. Parker Solar Probe's instruments were built to study the Sun itself and its corona, not to hunt for distant objects passing through the field of view. Its cameras point directly at the Sun or its immediate surroundings, so the chance of it randomly imaging a fast, distant interstellar visitor like Atlas is extremely low. To truly observe Atlas, Parker's observation plan and pointing direction would have to be reprogrammed specifically to align with Atlas's perihelion passage. That is technically possible, but it would require advanced planning and formal approval from NASA. Right now, there is no indication that Parker Solar Probe will be tasked with observing Atlas. The spacecraft is already running on a very tight primary mission schedule and diverting a Sun-focused mission to track something that might be a comet is not a decision that's easy to justify in terms of scientific priorities. So ironically, the one spacecraft that could actually see Atlas will probably not be looking at it. So the reality is this: in that 4 to 6 week interval from mid-October to late November, observations of Atlas will at best be intermittent, and at worst completely absent. We might get lucky. A spacecraft might, at just the right moment and in just the right direction, catch an image or spectral data, but it would be only a brief snapshot. Continuous tracking won't be possible. We won't be able to monitor Atlas's velocity in real time, and if the maneuver it performs doesn't generate a very large thermal or exhaust signature, we will find it nearly impossible to detect a subtle maneuver carried out during this period. This is what's called the detection gap, and this is exactly why October 29 is such a critical date. If Atlas is really going to perform a maneuver, fire its engines and change its orbit, it can do it in this window with the lowest risk of being observed. Not zero risk, of course. Juno or JUICE might pick up something, but the probability is lower here than at any other point in its orbit. Before perihelion, all major telescopes on Earth spent months observing Atlas and recording every parameter. After conjunction, when late November arrives, telescopes will look again, measure its position, measure its velocity and look for changes. But in that whole chain, there is exactly one period in which observation drops to almost zero, and that's this conjunction period. So, if the maneuver really did happen, what will we see? The answer is simple: not the maneuver, but the result. When Atlas emerges from behind the Sun at the end of November, astronomers will immediately turn their telescopes toward it and measure its position. then compare that to the predictions made from the pre-conjunction orbit. If Atlas is exactly where it's supposed to be, that means no manoeuvre was performed. But if there's a discrepancy, if Atlas appears slightly ahead of where it should be, or slightly behind, or even shifted off the predicted track, that is direct evidence of a change in velocity. The magnitude of that deviation tells us the size of the velocity change. For example, a small deviation of a few thousand kilometers would indicate a small maneuver on the order of a few ms or a few tens of ms. But if we see a shift of millions of kilometers, that would most likely mean a large burn of about 3 km, the amount needed for orbital capture. In the first few days and weeks after Atlas reappears, if these measurements are made, astronomers will be able to reconstruct its post-conjunction orbit. That way, they can tell whether Atlas is still on a hyperbolic trajectory or whether it has switched to an elliptic, sunbound, orbit. And they'll also be able to refine the new orbital parameters, semi-major axis, inclination, orbital period, and so on. This process is called orbit determination, and it's how we track every asteroid and every comet in the solar system. You measure an object's position at different times, fit those data points to an orbit using Newtonian mechanics, and as more data come in over time, you refine that orbit and make it more precise. For Atlas, the first few measurements at the end of November will be critical. Those measurements will almost immediately tell us whether something happened during solar conjunction. If Atlas's orbit is still an escape orbit, i.e. it matches the predicted hyperbolic path, then no significant maneuver took place. Atlas will be leaving the solar system as expected. But if the orbit turns out to be elliptic, meaning Atlas is now bound to the Sun and has a definite orbital period, then something happened. Something changed Atlas's orbit, and from that point on, only one question remains. What did it do? Was the change caused by a natural process or by a deliberate maneuver? That's what we'll have to figure out. One of the difficulties is distinguishing a deliberate maneuver from natural effects, because comets, by their nature, can maneuver slightly on their own. As ices on their surface sublimate when they get close to the Sun, i.e. turn directly from solid to gas, the resulting gas jets apply a small but continuous thrust to the nucleus, just like a rocket exhaust. The result is outgassing-induced acceleration. For most comets, this effect is very weak, but still measurable. Over weeks or months, it can change the object's speed by a few meters per second. If Atlas experienced similar outgassing during solar conjunction, that could slightly alter its orbit, with no advanced propulsion system involved, just a purely natural mechanism. In that case, Atlas would still be a natural object, just a bit more active and variable than it was before perihelion. But the reason Loeb believes outgassing can't explain a large orbital change on Atlas is very clear. Because pre-perihelion observations showed almost no non-gravitational acceleration in Atlas's motion. Yes, there were some signs of water vapor and other gases leaving the surface, but even so, Atlas's orbit fit the purely gravitational model with extraordinary precision. The data were so precise that the upper limit of the calculated non-gravitational acceleration was about 15 meters per second squared per day, i.e. very small when integrated. Compared to the 3 km velocity change needed for orbital capture, this is vanishingly small. In other words, outgassing simply cannot produce such a large maneuver. What's more, for this effect to suddenly increase 1,000-fold exactly at perihelion and to deliver exactly the needed delta V is a type of behavior never observed in any comet to date. Comets don't work like that. Their activity increases gradually as they approach the Sun, peaks near perihelion, then gradually decreases as they move away. But for an outburst of exactly the required magnitude to occur, exactly at perihelion is not consistent with any known physical model. There's also the direction problem. Outgassing matters not only in magnitude but in direction, because it produces acceleration in the direction the gas jets are pointing. On a rotating comet, these jets, depending on where the active regions are, can point in semi-random directions. One jet may push north, another east, another south. And in the end, these small forces tend to average out, and the net effect diminishes over time. A retrograde burn, however, i.e. a burn that reduces speed by thrusting opposite the direction of travel, requires a much more specific thrust direction. To achieve this without gassing, most of the jets would have to be pointed predominantly backward, i.e. opposite to the direction of motion. That's only possible if the comet's spin axis is aligned just right, so the rotation relative to the Sun, the distribution of jets, and timing would all have to line up perfectly. This is theoretically possible, but every such requirement adds another coincidence. And when you already have this many convenient coincidences stacked up, adding one more makes the natural explanation much less convincing. Therefore, if Atlas emerges from conjunction on an elliptic orbit, i.e. it has become bound to the Sun, the default hypothesis becomes very clear. Thrust was applied, something pushed it. The right force, at the right time, in the right direction, and orbit capture was achieved. In such a scenario, the question is no longer, is Atlas natural or artificial? The real question becomes, what do we do now? Because if an object chooses, deliberately, to enter solar orbit instead of continuing on into interstellar space, that is a message, a silent but clear message. I'm here, I'm not leaving, pay attention. Whether that message is friendly, neutral or threatening is a separate discussion. But in any case, the event fundamentally changes humanity's relationship with Atlas. It's no longer about watching an interesting interstellar visitor. It's about living with a permanent presence in our cosmic neighbourhood. Avi Loeb says that if Atlas is really captured into solar orbit, it will no longer be just an issue for astronomers. It will require a coordinated international response. That response doesn't have to be military, though some countries will certainly put that on the table, but at the very least a scientific and diplomatic framework will be needed. Are we going to try to communicate with this object? If so, with what protocol? What do we say in the first message? These are things that will have to be decided in advance. At the same time, we will have to assess whether Atlas poses a short-term or long-term risk, knowing full well how limited our data are. And we will have to think about the impact on society, how to announce it to the public, how different countries' different levels of intelligence and technology might generate geopolitical tension. But the meaning of all these possibilities depends on whether the maneuver actually happened. If, when Atlas reappears after solar conjunction, it is still on its original trajectory, i.e. is still heading out of the solar system, then October 29th will simply be a quietly passed date. In that case, Atlas is just a slightly unusual comet. It followed natural laws, it did what was expected, it didn't deviate, and we will have learned a bit more about the behaviour of interstellar objects from the process. Then, when the sky goes dark again, our telescopes will start waiting for the next visitor. Life goes on. It's this very uncertainty that makes October 29th so critical. That date is like a branching point, the moment when the future splits into two completely different paths. In one scenario, Atlas is just a comet. It follows natural processes, departs on its orbit, and we continue on our way with a little more admiration for the universe. But in the other scenario, Atlas is something else, and in that case, normal no longer applies. That moment becomes a turning point in humanity's cosmic history. We will find out which scenario we're in at the end of November, when Atlas reappears and we measure its orbit again. But whichever path we end up on, if this is really a choice at all, will already have been decided on October 29th, behind the Sun, in a place no telescope could see and no signal could reach. Now we've come to the point where everything converges, the manoeuvre window, the detection gap, the stacked probabilities. All of these pieces point to a single moment, October 29th, the moment that could change Atlas and maybe humanity's place in the universe at a fundamental level. And the most unsettling part is this. If something like that did happen, we'll only find out weeks later, not while it's happening, but after it's already over. If Atlas really did perform a maneuver, that is, if it changed its orbit during the solar conjunction window and was captured into a permanent orbit around the Sun, then the timeline of what happens afterward is extremely tight. The object would begin circling the Sun on its new elliptical orbit, and according to Avi Loeb's calculations, it would re-enter the inner solar system in late December 2025 or early January 2026. That means less than 3 months after perihelion. So when we finally see Atlas again and realise its orbit has changed, there will be less than 2 months left before its next pass. The time humanity would have to decide how to respond to a technological visitor would not be measured in years. It would be so short it could be measured in weeks. Loeb calculated in detail what a captured orbit would look like. If Atlas reduced its speed by about 3 km/s during perihelion, and thus switched from a hyperbolic escape trajectory to a sun-bound elliptical orbit, the characteristics of the resulting path would be quite striking. The orbital period, depending on the exact delta V applied, would be between about 8 and 12 years. The semi-major axis would be around 4 to 6 astronomical units, which means Atlas would retreat out to around Jupiter's orbit at aphelion, its farthest point from the Sun. But the perihelion, the closest point to the Sun, would not change. Atlas would still come as close as 1.4 AU, the point at which it performed the manoeuvre. Earth, meanwhile, orbits at 1 AU. This geometry leads to a simple but important result. Every time Atlas returns, on every perihelion passage, it will pass through the region where the orbits of Earth and Mars lie. In other words, from that point on, close encounters between Atlas and the inner planets become unavoidable. According to estimates, the first close pass could happen as early as December 20th, 2025. If Atlas was really captured into an orbit of about 8 years, on that day Earth's position along its orbit would be almost perfectly aligned with the path Atlas is taking inward. In that case, the closest approach distance would be about 45 million kilometers. That's roughly 30% of the distance between Earth and Mars when they're at their nearest. So there is no collision risk. It's still a safe distance in astronomical terms, but at the same time, that distance means a major opportunity, because at that point Atlas would be close enough that even amateur telescopes could see it not just as a point of light, but as a slightly resolvable object. Professional observatories could resolve shape details if Atlas has any surface structure. Radar systems could send radio signals from Earth and receive echoes from the object to measure its structure, composition and rotation. So this close pass wouldn't be a danger. It would be a historic observation opportunity, and if Atlas was truly captured by the Sun, this would only be the first encounter. This is exactly what Loeb was hinting at when he said, "Take your vacation before October 29th. Because if Atlas really is captured and approaches Earth in December, the world will change. Not physically, but perceptually, psychologically and socially. In a universe where an interstellar visitor says, 'I'm not passing through, I've settled,' humanity is forced to confront its oldest question. Are we alone? And the answer becomes clear. Apparently no, we aren't. Then comes the second question. Is the object intelligent? We don't know. But a maneuver implies intent. And the third most disturbing question, what does it want? We don't know, and that not knowing breeds fear, speculation and conflict. The geopolitical consequences would be felt immediately. Every country with space observation capability would race to gain access to the data. The US, Europe, China, Russia, India, Japan. All major telescopes would be turned toward Atlas. Data would be collected, analysed, compared, or withheld for strategic reasons. Some governments would argue for transparency, for openly sharing all findings so that humanity could have a unified response. Others would do the opposite, classify the data, treat Atlas as a national security threat or a strategic opportunity, and restrict information. And thus, for the first time in human history, while observing an interstellar visitor, we would divide not according to the truth, but according to our own interests. That fragmentation would be inevitable, and understanding what we're actually facing would become harder than ever. Then there's the communication question. If Atlas is truly a technological object, and the maneuver on October 29th confirms that it's a probe or spacecraft, then the unavoidable question becomes, do we try to communicate with it? This possibility isn't new. SETI, the Search for Extraterrestrial Intelligence, has had protocols for exactly this sort of scenario for decades. These documents outline in detail how humanity should act in the event of a confirmed detection of extraterrestrial intelligence. The protocols emphasize caution, international consultation, and especially avoiding hasty, unconsidered messages or sending sensitive information. But all of these guidelines are for radio signals coming from light years away, for distant, abstract encounters where the reply might come years later. Atlas, however, is here. It's inside the solar system. And if it really is a probe, it could be close enough to approach Earth within weeks. That is a completely different situation. It might not mean sending a signal, it might mean receiving one, or even meeting. SETI's protocols may have prepared us for a hello, but not for a visit. Some researchers would have no hesitation. Let's try to communicate immediately. Directed radio signals toward Atlas, mathematical sequences or universal visual codes that any technological civilization could recognize. For example, prime numbers, geometric ratios, or reference patterns based on the speed of light. For this group, staying silent is not the human way, speaking is, but others won't agree. Let's stay silent. Let's not expose ourselves before we know what this is. This opposing view holds that caution is part of survival. After all, we don't know who we'd be talking to, we don't know what they want or how they perceive us, and once we start talking, there is no way back. This debate will inevitably be fierce, and more importantly, there is no single authority to make this decision. The United Nations has no legal authority or pre-established mechanism for extraterrestrial contact. So any country, or even an individual institution, could send a signal without international consensus. And once that signal is sent, it cannot be taken back. Electromagnetic waves travel at the speed of light. It would take only a few minutes for them to reach Atlas 45 million kilometers from Earth. In that moment, the message sent would become the first word humanity has ever spoken to the universe, and we would never be able to unsay it. R.V. Loeb argues for a much more measured, cautious approach here. According to him, if it is confirmed that Atlas really has a technological origin, the priority should not be to communicate, but to understand. First observe, then analyze. Try to understand before you speak. Loeb says, in the first phase, what must be done is to collect as much data as possible about Atlas's structure, composition, and behavior. Watch whether it emits any radio signals or light patterns. Look for clues in its movements, in its energy output that might indicate intent, whether friendly, neutral, or hostile. Only after a solid foundational understanding is established should active communication be considered. And even then, it should not be the initiative of a single country, but an internationally supervised message whose risks have been clearly evaluated. Because Loeb's warning is simple, but profound. Sending a message is not just saying hello, it is revealing that you exist. Your location, your level of technology, even your weak points, all of that is embedded in the message. No matter how careful you are, the moment you communicate, you expose yourself. And Loeb's final line, "You can never know who is listening in space," is exactly what people push back on. Because the counter-argument is actually quite strong. We've already exposed ourselves. Indeed we have. Since the 1920s, our radio and television broadcasts, our air traffic signals, our radar, even the noise of our wireless communications have been leaking into space. These signals travel at the speed of light. As of today, they have reached a region about 100 light-years in radius. So any civilization within that distance with sufficiently sensitive detectors could already have figured out that Earth is a technological planet. If Atlas really detected those signals and adjusted its trajectory accordingly, that is, if it has already noticed us, then staying silent now has no meaning. They already know. There's no point in hiding from them, because we're already on their radar. So the question shifts to this. Will we make it clear that we know they know? Will we openly say, yes, we noticed you? Or will we act as if we haven't seen them watching us, and just keep playing our role on the cosmic stage as though nothing happened? This decision would, perhaps for the first time in human history, be a harder question than whether we are alone in the universe. This philosophical debate, communication or silence, will begin the moment we realize at the end of November that Atlas's orbit has changed. And in December, when the object makes its first close pass, that debate will no longer be academic. It will become a real-time crisis. Every day after that, if no response comes from Atlas, If there is no sign that it's interested in Earth, the tension will rise. Is it watching us silently? Is it waiting for us to make the first move? Or is it just a malfunctioning probe, captured into orbit by coincidence, no longer in contact with anyone? Or, even more unsettling, could it be refusing to respond on purpose? Maybe it's observing us like an anthropologist, delaying contact deliberately in order to minimize its impact on us, studying our behavior first. In that case, its silence would not be an absence. It would be a cold, deliberate strategy. This ambiguity will be extremely unsettling for humanity, because even after all these observations and analyses, we still won't be able to give a definitive answer to the question of what Atlas really is. Yes, we may see that its orbit has changed. We may rule out natural explanations like outgassing. We may gather strong evidence that a major maneuver was carried out. But even that will not prove that Atlas was sent by aliens, because the possibilities are far broader than that. Atlas could be an autonomous system that makes its own decisions, a von Neumann machine that replicates itself and roams the galaxy. It could also be very old. Perhaps it's a still functioning remnant of a civilization that disappeared millions of years ago. The senders may be long gone, but the mechanism, like a forgotten lighthouse, is still doing its job. Or perhaps Atlas is something that doesn't fit our definitions at all, something that can't be classified as biological or mechanical, something that represents technology or life in a completely different form. Maybe its mode of existence lies beyond the boundary of what we can make sense of, and while we're observing it, we're really just staring at the reflection of our own ignorance. The only way to answer these questions is to observe Atlas from much closer. And that's why the December encounter becomes more critical than anything else. If Atlas really comes as close as 45 million kilometers, that distance is suitable for radar imaging. For example, although no longer active, facilities like Arecibo or the still operational Goldstone Solar System radar, California, can send radio signals to objects up to about 50 million kilometers away and receive echoes. As those echoes return from the surface, they reveal the object's shape, rotation rate, surface roughness, and sometimes even clues about its internal structure. If Atlas's surface has antennas, regular geometric lines, or structures too orderly to be explained by natural geological processes, radar data could reveal them. The resolution wouldn't be perfect, on the order of tens of meters per pixel, but even that could answer the basic question: is this a rough, natural nucleus or a smooth, artificial shell? That distinction could answer the biggest question in human history. Optical imaging also becomes dramatically more powerful at that distance. If the Hubble Space Telescope can be brought back online for Atlas in December, it could achieve resolutions of a few kilometers per pixel from 45 million kilometers. That may not be enough to show very fine details, but it is more than enough to determine overall shape, to spot large-scale structures, and to derive composition from how the surface reflects light. If Atlas is truly a natural-looking nucleus made of a mixture of ice and rock, its reflection spectrum will be diffuse and dull. But if the surface is covered with metal or composite material, it will reflect light much more sharply and regularly, like the outer skin of a spacecraft. At that point, spectral analyses come in. Hubble or ground-based spectrometers can decompose the incoming light into wavelengths and look for traces of materials used in spacecraft construction, like aluminum, titanium, silicon alloys. If the reflection patterns of these elements are found, that doesn't just mean Atlas might be artificial. It means humanity would, for the first time, be directly observing the engineering of another civilization. There's also this. What will Atlas do during the close pass in December? That is perhaps the most critical of all the questions we've asked so far. Will it change velocity again? Will it adjust its orbit to match Earth's and enter a resonant configuration that brings it back at regular intervals? Or will it release something? Small probes, observation devices, or markers that detach from the main body and approach Earth independently? Or will it do nothing at all, just pass silently, moving on its elliptical orbit, unresponsive and expressionless, giving us no clue about its nature or purpose? The December 2025 encounter will be the first real opportunity for high-resolution data, but not the last. If Atlas has truly been captured into an 8 to 12-year orbit, it will revisit the inner solar system on every perihelion. That means that in the coming years, many new opportunities for observation and possible interaction will arise. With each return, we can learn a bit more, test our hypotheses, and deepen our understanding. But at the same time, each pass will bring back the same anxiety. If Atlas still remains silent, still emits no signal, reveals no identity, then humanity will have to face the same question every time. Is this thing watching us? Or is it simply here, on its own path, completely ignoring us? As we fail to get answers, the thin line between curiosity and fear will grow a little blurrier on every pass. Loeb directly links the Atlas scenario to the 2017 Oumuamua encounter, because Oumuamua was the first confirmed interstellar visitor in human history, and like Atlas, it disappeared as quickly as it came. Observations of Oumuamua contained a series of anomalies that couldn't be fully explained by classical comet or asteroid models. The object had an unusually long and thin shape, almost like a cigar or a disc. Also, as it moved away from the Sun, a small but measurable increase in acceleration was detected, and it couldn't be explained by the kind of outgassing seen in comets. More interesting still, its orbit showed that Oumuamua wasn't bound to any known star system, and must have been ejected from another star millions of years ago. At the time, Loeb used these data to propose a radical, but mathematically consistent hypothesis. Oumuamua could have been a light sail, a very thin reflective structure propelled by starlight pressure. That would mean it wasn't natural but artificial. This claim sparked huge debate in the scientific community. Many astronomers argued that natural explanations, for example, a low-density, loosely bound comet, were still more plausible, but none of them were definitive, because Oumuamua was travelling so fast that telescopes lost it before they could collect enough data, and it exited the solar system. In the end, we were left with only insufficient data, and the big question remained hanging. Was that thing natural, or was it a message? According to Loeb, Atlas could be the second act of that unfinished question. Atlas is different for that reason, because it may not leave. If the manoeuvre on October 29th succeeded, and the object was truly captured into a sun-bound elliptical orbit, we can study it for years, even decades, just like the natural members of the solar system. We won't have the "it was fascinating, but we lost it before we got enough data" problem we had with Oumuamua. If Atlas isn't escaping, we can go after it. We can send a spacecraft to it, match orbits with appropriate trajectory designs, and if international approval is secured, even land on it. We can place instruments directly on its surface, take samples, and analyse them in situ. That way, we won't have to base our decisions on a few hastily captured telescope measurements. We can base them on comprehensive, high-resolution, repeatable data. But this is where the human factor comes in. Sending a spacecraft to Atlas, trying to understand it, conducting international cooperation. All of that assumes that governments and agencies will put science ahead of security and rivalry. And history has shown us many times that this assumption doesn't always hold. When the Soviet Union launched the first artificial satellite, Sputnik, in 1957, the US didn't see it as a scientific achievement or an opportunity for cooperation, but as a geopolitical threat. So the first era of space exploration didn't begin with joint steps for humanity, but with competition, with the question, who gets there first? If it is confirmed that Atlas has a technological origin, it is very likely that a similar dynamic will emerge again. Countries may compete to be the first to reach, first to analyse, first to make contact. Some may seek political gain through technological superiority, or even through some notion of salvage rights. Others, on the other hand, may realise that this is no longer a matter for a single country, but an event that concerns all of humanity. The outcome will depend on who takes the lead and whether common sense prevails. If cooperation wins over competition, humanity may, for the first time in history, manage to unite in the face of an extraterrestrial intelligence. But if ego, nationalism, or the hunger for power outweighs that, Atlas could become the story of a first contact that pits us not against it, but against each other. And once again, we circle back to the same point. October 29th, the maneuver window. That single moment when everything could change, and that moment has already passed. It was 6 days ago. Atlas reached its closest point to the Sun and is now moving fast behind the star. Ahead of us is about a 4-week dark period, a period when no telescope, no observatory will be able to see it. During this time, we will have only our data, our predictions, and our probabilities. The only thing to do in these 4 weeks is prepare. Compile the measurements, update the models, and most importantly, be mentally ready to ask, is this thing we've been tracking really what we thought it was? Because after October 29th, the dice were rolled. There's no going back now. Either Atlas will continue on its way, and it will be confirmed that it is an ordinary or unusual but natural visitor, or it will enter a permanent orbit around the Sun, and we will have reached the threshold of something much deeper. We will find out which is true at the end of November, but until then, we can't change the outcome. The maneuver was either done or it wasn't, and that difference will determine the course of human history. The future will either continue along the line of we're alone, or it will silently, irreversibly veer onto the line of we were never alone. If you've made it this far, it means you've felt the weight of orbital mechanics, observational gaps, and the consequences of a visitor that might choose to stay. If you want to see more deep dives like this, don't forget to like and subscribe. Tell us in the comments, did Atlas actually make that maneuver? If it did, what does it mean? And is humanity really ready for this? Time has flowed. October 29th came. Atlas reached perihelion and slipped behind the Sun. Now all that's left is to wait. The end of November will show us everything. But until then, all we have are calculations, predictions, and the hope that we'll be ready for whatever we find when it reappears. The maneuver window has closed. The point of no return has been passed. And humanity, without even realizing it, has entered a new chapter. We will either learn that we are still alone in the universe, or that we never were. Sweet dreams.